Okay, on to number 2. Let's write a function that locally attenuates noise in a mesh through a diffusion process. To do so, we will approximate the Laplacian operator using the umbrella operator at a specific vertex. Then we will apply the approximated Laplacian to a given vertex to locally smooth the mesh around that vertex. This void function should directly modify the vertex v's position. Okay, so what does this actually mean? Well, we're going to take some vertex v, we're going to access the vertex's neighboring vertices and compute L. So that's right here. This is the Laplacian operator. Okay, and then, given the value of L, we're going to take our original vertex and we're going to modify the position of this vertex given this equation here. And this will actually, when applied repeatedly, smooth out high frequencies and kind of maintain the mesh's relative shape. So now that we kind of understand what this question is asking, how do we actually implement this? Okay, so we need to iterate over all of the neighboring vertices. So let's just draw out a similar diagram as the previous question and go through the operations that we're going to need to do. So let's say this is our initial vertex, and we need to access each one of these. Okay, well, our vertex will point to a half edge. Let's say it's this one. And our half edge will point to a vertex. So know that your half edge, although it connects to vertices, it's only going to have a pointer to one of the vertices. And the convention that we're going with is that the vertex that our half edge points to is the one behind it. So if you have a half edge pointing this way, it's always going to point to the vertex here. So this would be like half edge vertex. Okay, so keeping that in mind, we're going to need to first take our half edge, then get the next half edge, and take this one's vertex. So we have our original half edge is this one, and then we'll do next, then we access vertex, and then we need the next vertex. So that'll be next, oops, next, access vertex. Okay, and then we're going to want to go to the next triangle, so we're going to have to call twin, next, this will be another vertex access. Okay, let's just keep in mind we are here. This will be a vertex access. Okay, so now if you pay attention to this, we are actually accessing the same vertex as we did before. So these two are actually the same. So we don't want to have any repeat accesses, so we're going to take one away. And I'm just going to remove, this one, because this will make our pattern much more easy to implement. So since we took that away, we're actually already in the next loop, in the next like repetition of our accesses. So this will be our full pattern here. Okay, now let's actually write this in code. So as before, we have our do while, and our do while is the start is not, it's not equal to our current half edge. Okay, and we need to save our start half edge. So the half edge of our vertex. We need our current one. Okay, and now we're going to do something that loops. So we will call cur equals cur h dot next. So we're here now. Now we need to access our vertices, so let's just add a cur vertex. Cur v equals cur h vertex. So this is our access vertex here, and now we actually need to do an operation over this. So let's just look at the equation again. We want to do diff equals cur v minus v, so original vertex. Oh, and then one more thing, keep in mind that this is actually a struct, so we need to actually access the position. Okay, and we want to add this to our sum so that we can average it later. Okay, and then now we need to finish our loop. So we need to do cur h equals cur h dot next. That's this one, twin. Let me just make some space, so then twin. And then we will actually be back at our top here, so the top here will do the next, and then the access vertex. So that's all we need to do. Okay. So now that we have all of this, we've looped through all of the neighbors of our vertex. Then what do we need to do? Well, we actually need to calculate L. So L is going to be the average of all of our differences. So we already have our sum. And we're just going to divide our sum by, let's say, num neighbors. And now let's just make sure we are keeping track of our num neighbors here, just for later. Okay, now we have L. We're going to update the position. This is the final step. So v position equals v position plus k, which is given to us right there, times L. And we're done.